Alright, so are we ready to move on? And what we had to do here is graph the inverse of this function. So one thing that we should do with this before we start even making this function is think about some of the key components. Remember, when we get the inverse of a function, we're going to need that line y equals x. And then let's get some key points here on that parabola. And key points is where it crosses those grid lines right there, right? So now that we have those 5 points here, now we're just going to take the time and reflect those over. That line y equals x. So now we get this, and then we can connect those and we can make our graph. So there we go. I can think of one question now that we look at this, this parabola that opens to the left here in blue, is this inverse a function? What do you think? Yeah, this inverse is definitely not a function. The reason why this thing's not a function is because this thing doesn't pass a vertical line test, right? We drag a vertical line going around here, we're hitting that graph more than once. So sometimes when we look at inverses, those inverse graphs, those inverse relations aren't actually functions. But if we brought back the first example that we had, is that one in red, is that considered a function? Yeah, that one's certainly going to pass a vertical line test here. No matter where we drag that vertical line there on both the blue graph and the red graph, we're going to get a function there. We're only going to hit that graph once. By the way, just giving you a little tip for your calculus class, we call those these two different situations here, we call these one-to-one functions, where the original and its inverse are actually functions. Those are called one-to-one. So when that relation is also considered a function, we give this a little bit of special notation. Whatever the function was, whether it be f of x or g of x or h of x or whatever, we can use this notation here with that superscript there with that -1 up there. And we call that the inverse of f of x. So let's use this a little bit. Let's write some inverse functions. So functions that undo each other, what we call inverse functions. I'll give you a little bit of an example here. Consider this function here of f of x equals x plus 6. We can take an input in there. Say we were to put 3 in there in our little function machine there. So realize we're just doing 3 plus 6. Pretty simple answer, right? We get 9. Well, what an inverse function does is a function that can reverse and undo what we have here. In other words, if we have the input 3 going into f of x and getting 9, what that means is if we put 9 into an inverse function, it will undo it and take us back to where we started, giving us 3. What kind of a function, what would the function look like here in this particular example? Yeah, it'd look something like this, right? Where to go from 9 to 3, we just have to take our input and just subtract 6. So notice the relationship here between these two functions of f of x and the inverse of f of x. One just says x plus 6, the other one says x minus 6. So what we're doing here is relying a little bit on our Algebra 1 skills, and we're just looking at operations that undo each other. The opposite of adding 6 would be subtracting 6, and there we have our inverse functions. So one thing to keep in mind, ladies and gentlemen, is that an inverse function is not the opposite of a function. Notice that the opposite, a true opposite of x plus 6 would look something like this, right? Negative x minus 6. Take the opposite of x and the opposite of 6. Notice this function here is not like that. Those aren't the same. So it's all about inverse operations, and this is what gives students a lot of trouble going forward. But I want you guys to think about what we did earlier here with those two functions from our warm-up there. We have these two functions here. Notice that when we put a 2 into 3x plus 8, we got 14. Notice when we put a 14 into x minus 8 over 3, we end up getting 2. So what can we say about g of x in relationship to f of x? Yeah, we can just simply say that g of x is actually the inverse of f of x. So let's do this. Let's look at a given function and then let's write the inverse using inverse operations. So to find the inverse function, let's use the inverse operation. So if the function here is saying that f of x equals 2x, one thing you got to think about here is what's happening to x, and that's being multiplied by 2. So the inverse would be dividing by 2. So we can quickly, on a one-step situation like this, be able to write an inverse pretty easily. And there's also a pretty easy way to check this too. To check it, just come up with some just any number at all. Some numbers work better than others for a given situation. So definitely don't make the check hard on yourself when it comes to these numbers here. So if we put a 7 in for f of x, now instead of 2 times x, now we have 2 times 7, which gives us 14. In order to check to see if our inverse is legit, what we have to do is now take that inverse function that we just had here, which was x over 2, and we're going to take that 14 that we had right there, and we're going to make that the input into our inverse function. And notice what happened when you put our output as our input with the inverse. Notice we got 7 back. So that will happen with inverse functions. If you didn't have an inverse function, this would not happen. In other words, ending back where you started. So what I'd like you guys to do is let's give this one a try. Or better yet, let's do this one together, and then I'll let you do the next one on your own. So this problem here, a little bit beefier in terms of the complexity with the algebra, right? Not a one-step situation here when you look at x. So we're going to have to do multiple steps here in order to get the inverse. But the trick to doing all these steps here is having a clear understanding of our order of operations and how when we solve an algebra problem we're doing the opposite. So let's pull out our reverse order of operations, right? When you solve an algebra problem, you're really doing the reverse order of operations. You're looking to add or subtract first from one side to the other, then you multiply or divide, then you deal with exponents, or then work with parentheses if you need to. So let's take a look at that. The first thing to consider here when you're looking at this here is think about what happened to x, and think about what happened to x in the proper order of operations. According to this problem here, what had to happen to x first is we had to divide it by 4, and then we have to subtract 5. So if we're being asked to write the inverse here, here's what we're going to bring into the mix as well. Remember all these warm-ups that we did here where I had you guys getting y by itself? We're going to bring this back, and we're going to do that with these problems here. Notice that f of x, right here we talked when you guys were in your Algebra 1 class, and certainly we mentioned at the beginning of the year here, f of x means the same thing as y, doesn't it? So we're going to switch that out, and we're going to call that y. Now, do you remember also that when we were dealing with inverse situations when it was as a graph, we switched x and y. The cool thing is we can do the same thing here. Let's switch x and y right now. So now notice not the variable x is being divided by 4 and 5. Now y is being divided by 4, and then we're subtracting 5 from it. So let's get y by itself, just like we did in those warm-up problems. First thing we have to look for is the addition and subtraction. Notice what happened here is it was a subtraction of 5. So we undo that subtraction by adding 5 to both sides. So when we do that, now we're looking at x plus 5 equals y over 4. And then we move on, just like we're solving a normal algebra problem, right? So then we need to undo the division by multiplying by 4. Now, what happens on the right side is pretty self-explanatory. There's really not a whole lot of wiggle room there. You're going to get y, right? Because those 4's will cancel out. I'm going to leave that up to you with the left side. You can either leave it as 4 times x plus 5, I'm okay with that, or feel free to distribute it and call it 4x plus 20 if you wanted to. I'm good either way. And so now that we have y by itself, now we can slap that inverse notation on it and call it the inverse of f of x equals 4x plus 5. 4 times the quantity x plus 5. So how can we check to make sure that we've got this right answer again? Because you're always going to want to check this here, and I can't stress how important this is at this stage here, because students really struggle with writing inverse operations, and an easy way to check it is just to throw in a sample input. So if we put in 40, now like I said, some numbers work better than others, but the reason why I'm picking 40 is because it's a number that's easily divisible by 4. So if we did that, took 40 divided by 4 and got 10, subtracted 5, we'd end up with an output of 5. So then we take that output of 5 and we plug it as an input into the inverse function. And so what we are expecting to get is the original output that we had here of 40, and sure enough, when we do 5 plus 5 first and get 10 and multiply it by 4, we get 40. Kablam! We got it. Alright. So let's wrap up this second video segment with this. I'd like you guys to look at that example on your note sheet, and I'd like you to use some inverse operations. I'd like you to tell me what the inverse is of 5x minus 7. Try when you're writing your inverse to use that inverse f of x notation there. So when you finish this problem off, try and write something that looks like this. The inverse of f of x equals, and then blah, write that in there. So this video will end now, and then once we do our little closing video here, we'll go through the solution, and I have a couple more questions for you, and some things to think about.